5.2 Radioactivity Memo. Number 1. State what's meant by background radiation. Well, low-level radiation found all around us. B. Name 3 sources of background radiation. Well, radon gas, rocks and buildings, food and drink, and even cosmic rays. C. Name a device that can measure the rate of background radiation. Well, a device called a Geiger counter can measure background radiation. Number 2. Complete the table below. So we've got alpha, beta, and gamma, 3 types of nuclear radiation. Well, what's their nature? What are they made out of? Well, alpha is a helium nucleus, beta is a high-speed electron, and gamma is high-frequency electromagnetic radiation. Alpha has a very high ionizing ability, beta is medium, and gamma has a low ionizing ability. Now this affects the penetrating ability because alpha particles interact with matter so much, effectively that acts like a brake, and they have low penetrating ability. They cannot penetrate into matter very deeply. Beta again is medium, and then finally gamma, because it's not really interacting much with the material as it's passing through, has a high penetrating ability into matter. Both alpha and beta, because they are particles, are affected by electric and magnetic fields, whereas gamma, being an electromagnetic radiation, is not affected by these fields. Number 3, complete the following decay equations by predicting the type of radiation emitted. Well, first we've got uranium to thorium, and the nucleon number drops by 4, the proton number drops by 2, so it must be alpha. With polonium to astatine, well, again, if you notice the nucleon number has not changed, but the proton number has increased by 1, therefore it must be beta. Again, titanium to lead, we've got an increase in proton number, but the nucleon number has not changed, so it must be a beta emitter. From carbon to nitrogen on the top right there, the nucleon number again has not changed, but the proton number has increased by 1, so that must be beta. Polonium to lead, our nucleon number drops by 4, our proton number drops by 2, so we must be dealing with alpha. And then finally, mercury to titanium, we keep our nucleon number at 206, but our proton number increases by 1, therefore we must have emitted beta radiation. Question number 4, define half-life. Well, really there's 2 definitions that we can use. The time taken for half the atoms of the radioactive sample to decay, or the time taken for the radiation level count to drop to half its value once background has been accounted for. Well, here's a question that uses that kind of idea, is B. A radioactive sample is recorded to emit radiation at a rate of 850 counts per minute. 20 hours later, the emitted level drops to 250 counts per minute. Without the sample, the background count is found to be 50 counts per minute, so that's basically the background radiation. Find the half-life of the sample. Well, firstly, we need to subtract background from our values. So 850 is really 800 coming from the source, and 250 is really just 200 counts per minute coming from the source. So starting off with 800, so that's at 0, okay. What's half of 800 is 400, half of 400 is 200, so we had to do 2 half-lives to go from 800 to 200. If that time in total takes 20 hours, well, it's gone through 2 half-lives, therefore the time for 1 half-life is 10 hours. Finally, state the type of radiation source, alpha, beta, or gamma, used in the following. So for food sterilization, we use gamma radiation. In smoke detectors, we use alpha, and measuring material thickness, they use beta.